Field Manual 5499 Hydraulics, Headquarters Department Army, Distribution Restricted, approved for public release, distribution is unlimited. Chapter 1. Hydraulic basic. Hydraulics is the science of transmitting force or motion through a medium of the confined liquid. Hydraulic device is power transmitted. Push a confined liquid. Figure 1.1 shows the simple hydraulic device transfer the energy taken because of the quantity of the load. Quantity of the liquid is subject to pressure to operate liquid power system. The operator should have the knowledge of the basic nature of liquids. He should ask recover the properties of liquids, how they act under different conditions. Pressure and forces. Pressure is the force exerted within specific area. Force per unit area expressed in pounds per square inch. Pressure can be expansion, resistance. The compression of fluid is being squeezed. The fluid has been liquid or gas or vapor. Forces anything that tends to produce the modified push or pull motion expressed in pounds. Pressure, an example of the pressure of the air gas fills over the automobile tire as inflated and more and air squeezes into the it can hold. The inside of the tire resists the squeezing by pushing outward of the casing of the tire outward, pushing the air in the pressure, equalizing pressure throughout the confined area. The characteristics of any pressurized fluid, for example, the inflated tire over the outward push of the air is uniform throughout. If it were not, the tire would be pushed into odd shapes because of its elasticity. This is the major difference between gas and liquid. Liquid slightly compressed, figure 1.2, page 1.2. When confined liquid is pushed on and pressure builds up, the pressure is still transmitted equally throughout, but the containment of the fluid behaviors make it possible to transmit pushes through the pipes around the corners up and down with the hydraulic system that uses liquid. Alright, figure 1.1 shows a basic hydraulic device confined liquid in subject space and a weight. Because its near incompressibility makes this action instantaneous along the system in the full liquid. Pressure can be created with squeezing, pushing confined liquid only if there's a resistant flow two-way of the push of fluid with the action mechanical pump by the weight of the fluid. An example of the pressure due to the flow weights would be in ocean depth. The water weight creates the pressure which increases or decreases depending on the depth. By knowing the weight of the cubic foot of the water, you can calculate the pressure over the depth. Figure 1.3 shows the column of the water 1 foot square by 10 feet high. Equal weights of the 10 cubic feet. 1 cubic feet for the water weighs 52.4 pounds. Total weight of the water is column to 624 pounds. Weight of the bottom covers 1,445 square inches, 1 square foot. Each square inch of the bottom is subject to 101 and 144th of the total weight of 4.33 pounds. Thus, the pressure depth is 4.33 psi. You can also create equal pressure of 4.33 psi in a liquid using a pump of the figure shown in figure 1.4 on page 1.4. But before the pressure heads was the only way to expose the pressure measurement, it was expressed in feet of the water. Today, heat head is vertical distance between the two levels in the fluid. Figure 1.3 head between the top of the bottom of the water is 10 feet, which is equivalent to 4.33 psi. Therefore, each foot of water is equal to 0.433 psi. Earth is to the atmosphere extending 50 miles up. The air has weight. The air creates a head of pressure called atmospheric pressure for the column. The air square inch and the cross-section height of the atmosphere would weigh 14.7 pounds at sea level. Thus, the atmospheric pressure is 14.7 psi at sea level. The rule is atmospheric pressure is in. Or it shows the gas and compression, liquid resistant compression, and 1.2 for compressibility. 1.2 hydraulic basics. Most hydraulic systems significant. Figure 1.5, page 1.4 show the interaction. Hydraulic atmospheric pressure under the resets of the condition listed below. Diagram A indicates the diagram tube opens both ends with a place in liquid. The liquid will rise inside and outside of the proportion amount of the liquid displayed from the submerged tube wall. Diagram B, ends of the tube is closed with a place in liquid. Liquid level of the tube is forced down because of the air of the tube must occupy the space. Therefore, the liquid is displayed for the liquid level. The outside of the tube rises proportion to the volume of the cylinder wall. The volume of trapped air below the original liquid. The atmospheric pressure is 14.7 psi. Liquid outside of the tube is not heavy enough to force the liquid inside of the tube upward against the pressure over the trapped air, which is more than 14.7 psi. Diagram C, the upper end of the tube is closed, but some of the air is removed from the tube. This tube, the pressure within the tube less than 14.7 psi, partial vacuum, perfect vacuum would exist. All pressures within the tube could be eliminated. A condition but it never happens because of the liquid outside of the tube, subject to the full atmospheric pressure of the liquid is forced up into the tube. Satisfy the liquid, however, the liquid rises if it depends on the difference of the air pressure between the trapped air and the atmosphere. Force, the relationship of the force, pressure, and area. If air force is equal to pressure in psi times area in square inch. 1.3 shows a water column. Total weight 144 square inch, 4.33 psi, 2.7165 psi at 10 feet. 1 cubic feet of 62.4 pounds, 4.33 psi, and shows a 1 foot cube. Example figure 1.6 shows the pressure of 50 psi being applied with the area of 100 square inches. The total force is 50 times 100 equals 5,000 pounds. Pascal formulated with the basic law of hydraulics in the mid-17th century that discovered that the pressure exerted on fluid acts equally in all directions. The law of the shape of the pressure confined with the fluid transmitted undiminished. Every direction acts with the equal force on equal area of the right angles of the containers or walls. Figure 1.7 shows the apparatus of Pascal developed this law consists of two connected cylinders with differential diameters with the liquid trapped between them. Pascal found that the weight of the small position balance of the weight of the large positions along with the piston areas are in proportion to the weights in the small cylinder. The force of 100 pounds per square inch piston creates a 100 psi. According to Pascal's law, the pressure is transmitted in undiminished in every direction. In the larger figure 1 shows pump pressure area in 10 square inches, pressure 4.33 psi, the weight, and then the pump at the 4.33 pounds, area 10 square inches, pressure of 4.33 psi. It shows interaction of hydraulic atmospheric pressures A, B, atmospheric pressure B, and C. 1.4 hydraulic basics. So enlarge the cylinder 100 psi pressure of the small cylinder transmitted to an area of 5 square inches, which resolve with a force of 500 pounds. And the second piston of the force is multiplied by the 5 times mechanical advantage of 5 to 1. Using same factors, you can determine the distance the piston moves. For example, the small piston moves down with the 10 inches. Large piston will move with the 2 inches. Using the following to determine the distance. 2 is the distance the large piston moves in inches is equal to the force of the small piston in pounds times the distance of the small piston moves in inches divided by the force of the large piston in pounds. Example, figure 1.56 shows the force and pressure area 50 pounds, 10 inches by 10 inch squares, 100 square inches, 5,000 psi pounds per square inch. Determine D2, the distance the large piston moves is equal to force of small piston in pounds times distance of small piston in inches divided by force of large pistons, which is equal to 100 times 10 over 500, which is equal to 2 inches. And then it shows the Pascal laws at percent of the 10, 100 pounds, 1 square inch, 5 square inches, 2 inches, 500 pounds, 100 psi. 1.3 flow. The flow is the movement of the hydraulic fluid caused by the difference of the pressure of the 2 points. Hydraulic system fluid usually produces the action of hydraulic pump, a device for the continuous push of the hydraulic fluid with the 2 ways of measuring the fluid velocity and flow rate. Velocity of the average speed in which fluid particles move past a given point measured in feet per second. The velocity is important consideration sizing the hydraulic lines carried with the fluid between the components. Flow rate is the measure of how much volume of liquid passes at a point at a given time measured in gallons per minute with a flow rate determine the speed at which the load moves. Therefore, it is important to consider the power. And 1.4 energy, work, and power. Energy is the ability to do work expressed in foot-pounds. 3 forms of energy: potential, kinetic, and heat. Work measured for the accomplishment requires motion to make force do work. Power is rating doing work with the rate of energy transfer. Potential energy is energy due to the position of the object has potential energy in proportion vertical distance above the Earth's surface. For example, the water held back with the dam represents the potential energy because of the release of the water does not work. Hydraulic potential energy is static force. If the force is applied with the confined liquid as shown in figure 1.4, page 1.4. Potential energy is present because of the static pressure of the liquid. Potential energy of the moving liquid can reduce the heat with the energy released. Potential energy can also reduce the moving liquid when it transforms into kinetic energy. Moving liquid can therefore perform work as a result of static pressure and momentum. Kinetic energy is the energy the body possesses because it is in motion. Great speed with the greater of the kinetic energy of the water released by the dam and into the rush of the high velocity jet representing the energy of the motion. Kinetic energy, amount of kinetic energy is moving liquid directly proportional square with the velocity and pressure called the kinetic energy may be called the velocity pressure. Heat energy and friction. Heat energy is the energy a body possesses because of the heat with a kinetic and heat energy dynamic factor of the Pascal laws deal with sag pressure that do not include the friction factor. Friction and resistance relative to the motion between the two pipes of the liquid that flows through the hydraulic circuit. The friction produces the heat. This causes some of the kinetic energy to be lost in the form of heat energy. Although friction cannot be eliminated entirely, it can be controlled to some extent, but the three main causes of excessive friction in hydraulic systems are extremely long lines, numerous bends and fittings, improper bends, excessive velocity for using undersized lines, and liquid flowing through straight piping at low speed. Particles of the liquid may move in straight lines parallel to flow direction. Heat loss from friction is minimal. This kind of flow is called laminar flow. Figure 1.8 diagram A shows laminar flow. If the speed increases beyond the given turbulent flow of the development, figure 1.8 diagram B shows the turbulent flow. Laminar flow, and then figure B shows turbulent flow. Figure 1.9 shows the difference because of the pressure drops due to the friction potential points. B now should flow with the resistance free flow condition. Pressure at the point of B is 0. Pressure at the point of C is the maximum because of the head of the point of A. The liquid flows from point C to B with the friction cause of the pressure drop at the maximum pressure 0 pressure. This is reflected to C with decreasing the head of the points D and E. Relationship between the velocity and pressure between figure 110 and page 1A explains Bernoulli's principle, which states the figure 110 shows the effective friction of pressure A, B, C, and D and E and F. Passes A shows chamber 100 psi, 90 psi gauges. Passes C, chamber B. Sag pressure moving the liquid varies inversely with the velocity. The velocity increase with the sag pressure. The creep of the figure of the force of piston piston X insufficient to create with the pressure with the 100 psi in chamber A with the piston X, but moves down with the liquid force out with the chamber A, moves through passage C, reach chamber B with the velocity increases with the passage through C, because the same quantity of liquid passes through the narrow area, and at the same time the same 100 psi static pressure in the chamber A is converted into the velocity energy passes C, so the pressure gauge of the point registers 9 psi liquid passes C, reaches chamber B, velocity decreases in former rate indicated with the static pressure reading 100 psi. Some of the kinetic energy is converted into potential energy. Figure 1.11 shows the combined effects of the friction velocity chain with the figure 1.9 and page 1.7 the pressure drop minimum of the at C to 0 at B. At D the velocity is increased over the pressure head decreases at E. At head increases with the most kinetic energy given up with the pressure energy because of the velocity is decreased. At F the head drops with the velocity increases. A the to work hydraulic system flow must be present with the work, therefore exerts force into the definite device measured with the force multiplied distance. Power, the standard unit of power, horsepower with 1 horsepower is equal to 550 foot-pounds of work every second. Using the following equation to find power. Power is in horsepower is equal to force in gallons per minute times distance in psi times time of 1.714. Divided by time 1.714. Alright, and then this shows combined effects of friction and velocity changes A, C, B, D, E, F. Chapter 2, Hydraulic Systems.